Okay, sorry. Okay. Let's see. Oh, okay. Can I see this? Okay. Oh, 来た. Okay. Good. Okay. Thank you, ladies and gentlemen, and thank you for organizer to invite me in this nice conference. And I'm going to talk about some past work on my, so I titled is the physics of topological magnon in the magnetostatic regime. So this idea is bridging two different community. One is the magnonics, and the other is the quantum Hall physics. So let me briefly sketch the idea. So as you all know, the relativistic spin-orbit interaction, there's a lot of research effort on this relativistic spin-orbit interaction. And the major role of this spin-orbit interaction is to lock the relative rotational angle between the spin space and orbital space. Due to this spin-orbit locking, so the complex valued character of the wave function in spin space was transferred to the orbital space. And because of this transfer, so the wave function in orbital space acquire complex valued character. And this results in a quantum anomalous Hall effect in ferromagnetic insulator and topological insulator, blah, blah, blah. So there's a lot of interesting things that are happening last decades. But if you look into the nature, there is a lot of other type of spin-orbit locking interaction. So you can even see in the Maxwell equation, if you see the Maxwell equation, there's an inner product between a spatial gradient and magnetic moment. So in the presence of this inner product, you cannot freely rotate the spin space. If you rotate the spin space, you have to also rotate the coordinate space. So all the physics which come from the Maxwell equation in continuous media will also provide you the kind of spin-orbit locking interaction. So we are focused on this type of spin-orbit locking interaction. So magnetostatic wave is a magnon, which is mainly propagated by the magnetic dipole-dipole interaction. And magnetic dipole interaction is nothing but this kind of spin-orbit locking interaction. So we can expect that in this magnetostatic regime, so the magnon can be very topological. So this is the outline of the talk. I will first briefly introduce what is the magnetostatic spin wave, and then I will briefly summarize the topological idea, our theory proposal, and then give the model calculation, and then I will explain how this model calculation can be seen in micromagnetic simulation. And then I'm switch into a relatively recent study of our group, in which we study the disorder effect on this topological magnon, where we have a nice picture of integer quantum magnon Hall plateau-plateau transition. And based on this knowledge, we further discuss how the thermal Hall conductivity should be given in this quantum magnon Hall system. So these are reference. Okay, so let me begin with the Landau-Ristić equation, which is the basic equation of motion for the magnetization. So the magnetic moment was driven by effective field, and this effective field comprised of dipolar field and exchange field. And the dipolar field are determined by the Maxwell equation. But when the speed of light is much faster than the typical spin wave velocity, we can use the magnetostatic approximation so that we can omit this part to be 0, and then the dipolar field is given by magnetization. So the whole equation becomes closed equation of motion for magnetization. And then in this Gaussian unit, if you see this part, you can see that magnetization has the same engineering dimension as the dipolar field. So therefore, the coefficient in front of the exchange field has a dimension of length square, which we call exchange length. And this exchange length is typically very small, like nanometer scale, because this exchange interaction comes from the quantum mechanical origin. So therefore, when the wavelength of the spin wave is much larger than the exchange interaction length, then this spin wave wavelength come up to here as a derivative, so that when the lambda is much larger than the exchange length, then the dipolar field is more dominant than the exchange field. And then, as I said, dipolar field is a spin-orbit locking interaction, so that if you can control the spin wave wavelength, you can actually enhance the spin-orbit locking interaction, so that magnon become more topological. So that's the idea. So to summarize this part, so if you go to the very small wave vector, so then the spin wave are mainly driven by dipolar interaction, and this is called a magnetostatic regime or dipolar regime. And although everything becomes very topological here, there's a trade-off, because the K is very small, so the energy scale becomes also very small. So the typical energy scale of the dipolar regime is a gigahertz or sub-gigahertz. But nonetheless, there's a research community who study the spin wave here. The people there is called Magnonics. And then the people in this community are studying how the spin wave propagate in this magnetostatic regime. And it is a research community with long history. And nowadays, they want to functionalize this magnetostatic spin wave. And main things what they're doing is they utilize the idea, borrowing the idea of the photonic crystal. So they make a magnonic crystal. So namely, they're making a periodic structuring in a ferromagnetic thin film. So this is the top view of the pattern structuring made by them. And then by making these things, so they have a magnonic band, and then so you have a band gap of the magnon band. So this is a picture obtained from the Brilliant light scattering. So you see there's a band gap for the magnon spin wave. And so schematically, so I can summarize the result like this. So if you make a periodic structuring, then this spin wave band will be holded at the zone boundary. And the zone boundary was specified by the reciprocal vector G, and which is determined by the length scale of the periodic structuring. So if you choose the length scale of the periodic structuring in very long, like microwave scale, then all the spin wave band you have is in a dipolar regime, and they are mainly driven by this dipolar interaction. So this is what I want, and then so therefore, and then so to discuss more concretely, so we need to begin with the Broad wave function for magnon band. So this band will have a Broad wave function. The J is the band index, K is the momentum, and then as you all know, so this topological number given as an integral of the Berry curvature. And this curvature is determined by this Broad wave function. There's a small comment that the inner product between these two Broad wave functions are always accompanied with this strange matrix, 2x2 matrix sigma 3. So this is because most of the magnon system, there is no U1 spin rotational symmetry, because the spin orbit locking interaction reduced the symmetry into lower symmetry, so there is no continuous spin rotational symmetry. So as a result, the magnon Hamiltonian is like a BDG Hamiltonian. So the Broad wave function for magnon is usually a linear combination of particle type and Hall type state. So it's exactly like BDG Hamiltonian for superconductor in fermion system. But unlike the fermion system, so the boson creation operator and annihilation operator are commute instead of anti-commute. So because of this commutation relation, so we need to have a 2x2 Pauli matrix in this particle Hall mixed space. And okay, yeah, so this is small comment. And then, nonetheless, once we have an integer, so we can discuss what kind of symmetry allow us to have this finite Chan number. So first of all, as I said, we need a spin-orbit lobby interaction. And then beside, we need a perpendicular magnetization. So first of all, if you don't have any spin-orbit locking interaction, so then you have a time reversal symmetry plus rotation only in a spin space. So if you apply time reversal symmetry, so then the moment is reversed, then you can apply spin rotation only in a spin space, so that make it back to the original state. So this symmetry allow you to have this relation, and then your curvature in a k point and the curvature in minus k point are opposite sign, so that the Chan number is always 0 because of the cancellation. On the one hand, if you have a spin-orbit locking interaction, then if you do time reversal operation, then the moment is opposite. But then if you do the spin rotation around the in-plane axis, then since we have a spin-orbit locking interaction, so the coordinate space should be also rotated by pi. So this coordinate rotation makes one of the momentum to be another minus sign. Because of this, so the curvature in this point and the curvature in this point is the same sign. So there's no cancellation between curvature. So because of this, so we are interested in this situation in which we have spin-orbit locking interaction and perpendicular magnetization. So I already explained that to have a spin-orbit locking interaction, we are mainly focusing on the dipolar regime in which the driving force of the spin wave is a magnetic dipole-dipole interaction. And then to have a perpendicular magnetization, so one thing you can do is apply strong magnetic field perpendicular to the plane, or use the perpendicular magnetic anisotropy, which come from the surface magnetism. Yep. Yes. Yeah. Spin-orbit locking interaction, I mean dipole-dipole interaction. Yeah. Okay. And then once you have a Chan number, then we can borrow a lot of knowledge in quantum Hall physics. And then so we can argue that once you have a Chan number, finite Chan number for the spin wave bulk band, then there is always a chiral H mode for spin wave, which go across the band gap for the bulk band. And then the number of the chiral H mode inside a given band gap is given by sum of the Chan number over particle band below this band gap. And then we can moreover discuss that we can also show that thermal magnon conductance along this chiral H mode are robust against elastic backward scattering. And this is a summary slide of a model calculation which I did for a while ago. And these two are top view of the thin film structure which I studied. And this blue region is a ferromagnetic area. And then these two are from this system, and then this are from this system. And then these two are a side view of the bulk spin wave band. And the red color specifies a band which has a -1 Chan number, and the blue colored band is a spin wave bulk band which has +1 Chan number. And then as you see, and then this one is a spin wave band calculation with open boundary condition. And then this blue color and red color line correspond to those spin wave which is localized around the boundary. So if you compare these two, you can see that indeed, if you have a Chan number for the spin wave bulk band, then you have a chiral H mode, and then whose sign is determined by the sign of this Chan number. And at this moment, there's no experimental real experiments for this model calculation. But I can show you a micromagnetic simulation result for this model calculation, from which you can understand how this kind of chiral H mode can be experimentally seen. So this model simulation was done by one of my collaborator, Oe-san. And this is the top view of the two-dimensional pattern structure which he studied. And he applied a static, so this black color region is a ferromagnetic region. And then he applied perpendicular to this plane, static external field, so that all the moments are perpendicularly polarized. And then he applied a spatially local pulse field at t equals 0. And then let the magnetization evolve in time based on the Landau-Lissitz equation. And then after pulse field is applied, he measured the transversal component of the magnetic moment as a function of t and space, whose linear combination gives you the kind of creation field for magnon. And then he take a Fourier transformation of this magnon field, by which he got the energy resolution of the magnetic excitation. Namely, amplitude of this field basically corresponds to a local density of state of magnon at given omega. So if you take a summation over all xy is a coordinate in this two-dimensional space, then you basically have a kind of density of state of the magnon. So these two figures shows a comparison between micromagnetic simulation and my spin wave calculation. So this left figure is a counter plot of the integrated power spectrum. So this quantity is called integrated power spectrum. So he plot the counter plot of integral power spectrum as a function of magnetic field. And we only consider the field is above saturation field. And this is the density of state calculated from our spin wave calculation. And then if you compare these two, this is nice consistency. And then in our model calculation, so this colored part comprises two bulk bands, inside which I have a band gap. So this actually corresponds to these two bands, inside which I have a chiral H mode. And so this calculation was like external field that is 0.2 times larger than saturation field. So that corresponds to roughly here. So basically, if I see in his simulation around here, I should see some chiral H mode. So that's what we did. So we put Hz equal 800 around here, L state. And then what we did is two things. We apply the local pulse field around the center of the system, so that certainly excites the bulk band. And then we obtained the integrated power spectrum. So that was obtained, that was plotted in this black curve. So in fact, I have two bulk bands, as I said. So correspondingly, I have two big peaks, and inside which I have a bulk band gap. And then we also apply a pulse field at the boundary of the system. So that would certainly excite the spin wave edge mode. And then so the density of state would be different from the case we apply for the center. So therefore, when we apply the pulse field at the boundary, then I obtain the integrated pulse spectrum depicted by this red color. And then, in fact, we have our peak in a bulk band gap area. So this would be a chiral H mode. So to see this more clearly, we further show the spatial resolved power spectrum. So this point, if I choose this particular frequency, and if I plot the spatial resolved frequency, the intensity are all localized around the boundary. And then if you further evolve in time, so this actually moves this way. So it has a chiral motion of the spin wave propagation. And then these two are indeed bulk band in the sense that are extended over all bulk. So this proves that our simulation can be seen, like our model calculation can be justified by the simulation. And then this is nearly same as experiments. So then, yeah, I'll move on the next part. So next part, I want to talk about the disorder effect on the topological magnon. So here is a list of quasi-particle boson analogs, integer quantum Hall phase, which was proposed last 10 years. So one of the first pioneer work was this Halden's photon. And so we also did a pioneer work on the magnon. But there is also many other quasi-particle boson. And then if you look into this literature, so the people all believe that the quasi-particle boson flow along the chiral H mode, they all believe that it is robust against any elastic backward scattering. But here, I want to ask the question that, is it really true? And the question for asking, for reason for asking this question is as follows. So the robustness of the chiral charge transport along the edge state in integer quantum Hall state usually assume the electron charge conservation. In other words, if you don't have U1 symmetry associated with the charge conservation, so two integer quantum Hall state with different charge integer are no longer separated by the direct phase transition with delocalized bulk state. They can be crossover from one to the other because the charge transport along the edge is not protected if you break the electron charge conservation. But if you see the Hamiltonian for this system, you notice that even at the level of quadratic boson Hamiltonian, so the Hamiltonian has no explicit U1 symmetry at all. So for example, in ferromagnetic magnon case, as I said, the U1 symmetry associated with magnon number conservation is nothing but the spin rotational symmetry around the SD, and which is easily broken once you introduce a spin orbit locking type interaction, such as DM interaction, dipolar interaction. Therefore, from the symmetry point of view, most of these Hamiltonian are described by those Hamiltonian which has no explicit U1 symmetry. So that we should fairly ask the question whether its quasi-particle boson flow along this chiral H mode are really robust against particle number non-conserving type disorder. So to answer this question, we study a two-dimensional spin ice model. This system was experimentally realized in a pattern ferromagnetic thin film by these people in Penn State. And here is a schematic picture of their experimental situation. And then due to the magnetic, so this blue region is a ferromagnetic island whose size is like micrometer scale. And then they comprise two island. One is elongated x direction, the other is elongated y direction. And due to this shape anisotropy, so the magnetic moment in this ferromagnetic island want to be polarized has a strong easy axis anisotropy along this elongated direction. And then if you further increase dipolar coupling between this ferromagnetic island, then you will have a so-called 2-in, 2-out ice rule for each vertex. And then this 2-in, 2-out ice rule give you a very strong frustration in a classical spin energy, ground state program. And as a result, you have a large residual entropy due to this spin frustration. So these were studied by these people, and experimentally it is indeed observed this large residual entropy. And then what we are interested in by taking this system is we want to apply field out of plane direction and make the classical spin configuration to be fully polarized along the out of plane direction. Yeah, sure, 5 minutes, okay. And then we want to study the spin wave structure. So, and then we find that the lowest two band for this model, when you apply sufficient strong saturation field, then the lowest two magnon band will have a finite Chern number, and then in between there's a chiral H mode. So we take this model as an example and then introduce a disorder and then study the localization, delocalization phenomena of the topological magnon. So yeah, so based on this model, we consider to introduce a disorder into a quadratic magnon Hamiltonian, which breaks the U1 symmetry completely. And so to be more specific, we calculate the eigenwave function of this magnon Hamiltonian, which belongs to the eigenenergy E. And then we set this eigenenergy E inside the topological band gap. So we set this E in here, in this area. And then studies how this eigenstate is localized along one direction. And so in the clean limit, in the clean limit, we are in a quantum magnon Hall regime. But if you have very strong disorder, so which completely destroys this band picture, then you should have a conventional magnon localized regime. So the question we want to ask is, when we're changing the disorder strength, what will happen between this quantum magnon Hall regime to conventional magnon Hall regime? And this is what we obtain. So this is as we plot localization length as a function of disorder strength. And then we see that these two regimes are separated by a quantum phase transition point at which the normalized localization lengths show a scale invariant behavior. So this suggests that the magnon Hall conductance in this quantum magnon Hall regime is probably very robust against elastic backward scattering. And then this is indeed what we see in a two-terminal thermal magnon conductance calculation. So here, we calculate the thermal magnon conductance along one direction, while the other direction we impose either open boundary condition or periodic boundary condition. When we impose a periodic boundary condition, then the magnon conductance is carried only by bulk state. For that cases, what we find is the conductance are almost always zero, except for this quantum critical point. So the bulk magnon wave function are all localized in either quantum magnon Hall regime or conventional localized regime. And then on the one hand, if we impose the open boundary condition along this direction, so conductance is also carried by H transport. And what we see in that calculation is so H magnon conductance are quantized to be 1 over H in this quantum magnon Hall regime. And then at this critical point, it drops to 0 in thermodynamic limit. So this already suggests that the magnon conductance along the H is very robust, at least within this quantum magnon Hall regime. Although you don't have any U1 symmetry in Hamiltonian level. So this suggests us the physics here is pretty much like a quantum Hall physics. So we basically have in a two-dimensional phase diagram subtended by disorder strength and the energy. We have two regimes. One is a quantum magnon Hall regime, and the other is a conventional localized regime. And then inside this quantum magnon Hall regime, so in both regimes, the bulk magnon wave function is localized, so they don't contribute to thermal conductance. But quantum magnon Hall regime, you have a robust H magnon conductance. Okay, so this is what we obtain. And based on this, so we have an argument why this robustness comes from. So essentially, so this robustness is simply means that this is because the energy conservation. So the disorder, elastic scattering do not change the energy. So this quantization is nothing but the thermal energy current is conductance is quantized. So that we discussed here. And then based on this picture, we further discuss how the thermal conductivity should be given in a disordered quantum magnon Hall regime. So in a clean limit, the thermal Hall conductivity is expressed by this way. So this omega is a Berry curvature, and the C2 is some non-analytic function. G is a Bose distribution function. So this was shown by these people. And then with this order, you don't have momentum K, so we need to think about the H transport picture. So to consider this situation, we again consider same geometry. So we make this direction open boundary, and then make this introduce a thermal gradient along this direction, and calculate the Magnon energy Hall current density along this direction. So first of all, in this case, what we find is for given disorder strengths, so I have a phase diagram as a function of E, and then this E corresponds to our energy for the single particle state. And all these single particle state will be contribute kappa xy for this given disorder strength. So they should be integrated out. But what we find is that all the bulk wave function except these two critical points are localized, and they do not give rise to the Magnon thermal conductance, so that we ignore them. And then on the one hand, between these two critical points, I have a sub-extensive number of H mode, which provide a quantized Magnon conductance. And the quantization is 1 over H. Therefore, then remember that conductance times dE is nothing but a Magnon current carried by Magnon state within this energy window. Therefore, a Magnon energy current density carried by H mode within this energy window is given by E times dE divided by Hm, where m is length along this direction. So therefore, Magnon current density carried by the H mode at the high temperature side is given like this, and the Magnon energy current carried by this side is given like this. And we can take summation over these two, and TL difference between TL is proportional to m, so this m is cancelled in here, so that eventually the total current density is given by a proportional to the round yt, and then the coefficient is expressed like this. And then, so again, I have a non-analytic function, which is same as the previous one. And then we can further generalize this argument to in more general Magnon, disordered quantum Magnon Hall system case. Epsilon 1, epsilon 2 is a critical point, two pair of critical point of bulk wave function which bound the region of the H mode. So from here to here, you have a H mode. Yeah. So I just integrate from here to here. Yeah. So that's how I get this and this. And this expression are actually consistent. If you consider temperature is much larger than the bandwidth of the Magnon, then this expression reduced to a previous expression of the kappa xy in the clean limit. So namely, if the temperature is larger than the typical bandwidth, I can maybe replace this energy encoded in this Bose-Dirichet function by a center of the bulk band, which is correspond to this E1, E2 things. Then I can freely take the k integral here, so which make this to be integer. So then this formulation back to this guys. So these two become consistent when the temperature is high compared to the bulk Magnon bandwidth. So this finalizes my talk. So I introduced this magnetostatic spin wave, and then discuss the review the concept of topological Magnon, and then review the and then I talk also about the recent progress about the disorder effect on topological Magnon, and then I give expression for thermal Magnon Hall conductivity in disorder system. Yeah. Thank you very much.
Thank you. Questions?
Thank you for a very interesting talk. I'm a bit confused about